All right, you crazy ape students. So we're going to delve into chapter 3, and we're actually going to start with section 2. I wanted to get you guys in the lab, and the supporting kind of fundamental energy stuff we want to talk about is actually in section 2. We'll get to section 1 later, but should be a relatively short lecture. But the stuff you guys did in the lab is going to rely heavily on the upcoming information. All right. So chapter 3 is about ecosystems and energy and the fundamental energy stuff. Before we even get into what ecology is and how energy plays a role there, is what we're going to look at first. Okay. So first of all, textbook definitions of energy, right? Energy, if you go to a physics class, they're going to call it the ability or the capacity to do work, right? And so for something to cause something else to happen requires some energy. All right. And you guys have probably heard, these various forms: chemical, radiant, thermal, mechanical, nuclear, electrical, right? All those are different types of energy, but really all types of energy really fit into two categories, right? That energy could be potential, right? Energy that's stored that has potential to do work, or kinetic energy, which is energy of motion, which is actually energy being used to do work of some sort. Okay? And so, this little diagram over here shows a pretty good kind of illustration, right? So that arrow, right, in that top bow here has stored energy, right? So essentially that's stored mechanical energy. Okay? So because that's pulled taut, really, as soon as that person lets go, that potential energy in that stored mechanical energy is going to get released and transform into kinetic energy in that moving arrow. All right. Kinetic energy, right, is motion. So that could be waves. That could be motion of electrons, atoms, molecules, substances, objects, right? So electrical energy is the flow of electrons through some sort of conductor. That's movement of electrons. That's kinetic energy. Radiant energy is typically referring to some sort of electromagnetic radiation. Actually includes heat, by the way, but light, sound, X-rays, gamma rays. Thermal energy is part of that radiant energy. Any sort of motion, so a moving ball, moving water, whatever, and sound, right? Those are all forms of kinetic energy, which again, kinetic energy is energy being used for something. All right. Now, potential energy is stored energy, and it has to do with the energy of position, right, or gravitational energy. There are several forms of potential energy. So gravitational energy. So if I'm holding an object above the ground, right, there is potential for that object to fall as soon as I let go of the object, right? That is that gravitational potential energy. Okay, nuclear energy. So the the nucleus of atoms, right, has potential. That's where most of the matter of the atom is. There's potential to convert some of that matter into energy, right? And that's the nuclear energy. You guys will hear a lot more about later on in the year. Stored mechanical energy, like a spring pull, or that bow and arrow example where we pull the string of the bow and arrow but don't let go. That energy has the potential to do something, but it's not being used. And then chemical energy. So you got to think about the food you eat, for example. As that food is sitting there, it's stored in the bonds of the molecules that make that food up, right? And so when we digest that food and reassemble it to make new materials, we're actually accessing and releasing some of that energy that was being stored as chemical energy. All right? So thermodynamics is the study of energy and its transformations, right? So as we go from potential to kinetic or vice versa, right? What's happening to the energy? What type of transformation is occurring, and what's happening to the quality or quantity of that energy in those transformations? All right. Now, first of all, we have to understand a couple kind of dictating ideas here. So first of all, are we talking about a closed system? Okay, a system in which case the energy does not get exchanged with its surroundings, right? Now, truly closed systems are exceedingly rare. In fact, you'd probably argue that truly closed systems don't entirely exist. The best example I could probably give you guys of what's trying to be a closed system is like a thermos bottle, right? So the idea of a thermos bottle is you put either a hot liquid or a cold liquid inside the thermos, and the intention is to try to keep it at that temperature by not allowing either heat to get in the case of trying to keep a cold liquid cold, or not allowing that heat to escape, in which case you're trying to keep your coffee hot or something. All right. But of course, we all know that if you leave a thermos bottle out long enough, eventually there's some energy exchange and the hot liquid gets cools off or the cold liquid warms up. It just takes longer. All right. And an open system is which case the energy is being freely exchanged with the surrounding environment. And again, most systems are somewhere on that spectrum, maybe not entirely open, maybe not entirely closed. There's some insulation, but not very much, whatever. But we have to kind of understand whether we're talking about a more or less closed system or a more or less open system, maybe is a better way to put that, okay? And why that's important will come up here in just a second. All right? So let's look at the laws of thermodynamics, and these are going to be things that you guys pull into your lab report, all right? So first of all, we have what's called the first law of thermodynamics. And essentially, you guys have heard this one, I'm sure you've heard this one before. It's energy cannot be created or destroyed, okay? And so in the case of, the first law, we're talking about, if we look at ecology, since that's going to be our topic of study this chapter, organisms cannot create the energy they need to survive. They need to capture it from another source. Now, you and I would capture that energy, of course, from our food. We eat something, whether it's plants or animals or some sort of animal product. There's stored energy in that chemical energy of that food, and we access that energy. But we can't create it ourselves. Plants, you guys sometimes is referred to as plants making their own food. Well, again, they're not creating that energy. You guys should all know by now that plants in reality are using sunlight, all right, and using the energy in the sunlight to then make their own food. So they're not creating their own energy. They're using energy from the sun to then create chemical energy, essentially, or store chemical energy in the form of some sort of sugar or something like that, okay? Now, so with the first law, the focus is on the quantity of energy. Now, if you take this to its logical end, then the total amount of energy in the universe is a constant, right? We're not losing energy. Now, it does transform, and we could say, some of it becomes matter, some matter becomes energy, which is kind of what's happening in a fusion reaction in stars and so on. But we're not creating energy. We're not losing energy. It gets transferred. It gets transformed to a different type. It goes from potential to kinetic or vice versa. Okay? So first law of dynamics, we're talking about that quantity. We're not creating energy. We're not truly losing energy. It just transfers or transforms. All right? Now, the second law of thermodynamics, and this is the kicker for ecology. Okay? So, we got that first law in place. It states that all energy transfers and transformations result in at least some of the energy being lost or degraded to the surrounding environment. Now, again, we're not truly losing energy. It's not going away. It's just essentially becoming unusable for us because it usually gets degraded into some form of heat, and heat's really hard to capture and make use of, by the way. So sometimes we say that heat is highly entropic, right? So entropy, okay, in the case of heat, right, is referring to the tendency for energy to become less organized over time. So when we say something's entropic or highly entropic, that means it has a tendency to degrade really easily, become disorganized. Okay? And so sometimes the second law of thermodynamics is also referred to as the law of entropy. Okay? In which case, over time, without the constant input of more energy, things become less organized or disorganized over time. And a way to think about that is, let's say, your bedroom at home, right? To keep your clothes in your drawers nicely organized, or to keep your bedroom clean, you have to input some extra time and energy into the organization. The tendency would be, without that added input, for your drawers to become more messy over time and your room to become messy over time, right? So keeping things organized and usable actually requires extra energy input. Otherwise, entropy takes over, and things become less organized over time. My desk at work is a great example of that. It takes time and energy for me to keep the paper straight, and not let things get overloaded, which can happen really easily. Okay, so some other things to consider is there's also no perfect transfer of energy. So if I have, let's say, my stovetop at home, heating up a pot of water or trying to fry some eggs or something, right? The heat energy from that stovetop is being transferred to the metal in the pan, which is then being transferred to the egg, essentially, if I'm frying an egg. Now, each of those transfers results in some of that energy being lost to the air in my kitchen, essentially, as heat. So there's no way in nature to come up with a perfect transfer. Okay? And likewise, like I talked about, with there being no truly closed system, there's no such thing as a perfect insulator. We've got some really good insulators, but there's always going to be some transfer of the energy in one object to its surrounding environment. Okay? So really here, the focus of the second law of thermodynamics is on the quality of that energy. All right? So a great thing to do, just to demonstrate this, is when you plug your phone in to recharge it, right? You should notice that the little adapter you're using actually, as the plug-in heats up, as does your phone itself. You guys should notice a little bit of heat being generated in that process. Now, the reason for that is the electricity that comes from the outlet in the wall. It's a highly organized form of energy, by the way, electricity is. Okay, that's being used to essentially shove some voltage and amperage into what's probably a lithium-ion battery in your phone. Now, during that process, some of that electrical energy is being degraded into heat. So not all of the energy being pulled out of the wall is actually going into your battery. Much of it is. Probably somewhere between 80 and 90% of that electrical energy is actually going into your battery and being stored there. But some of it, because there's no such thing as a perfect transfer, is actually being degraded into heat. Okay? And the same thing happens inside your body. When you guys eat food, there's no way for you to get all of those calories from that food and make use of them. Some of them degrade into heat. All right. And in fact, the more energy we try to access from our food, the more heat is generated. Part of the reason when we exercise, what happens? Our bodies heat up, right? Because we're creating a lot of excess heat. That heat, though, a lot is not really useful to us. It just kind of gets radiated out into the room around us. Okay. That's why my room gets really hot when there's 32 people in it. All that waste heat from those energy transfers are heating up my room. Okay, and then eventually that heat escapes outside and it's no longer usable to us. Okay, so that is the gist of what you guys need to have in place to kind of help finish up your lab reports in class tomorrow. Okay, so you guys will be doing that lab where you heated the water, right? You did that in class, and I think I told you in class I wanted you guys working on the lab reports after you've watched this lecture, and hopefully read those pages from the beginning of, from section 2 of chapter 3. Just some follow-up to this stuff, all right? So some things to think about as you close up this first lecture of chapter 3. Number 1, is the Earth an open system or a closed system in reference to energy? Okay. 2, is the Earth an open or closed system in reference to matter? So is the energy we're getting to the Earth, is that continuously coming in and leaving, or is it just locked in place? 2, in terms of the matter, so that the carbon, the minerals, etc., that make up the Earth, are we gaining and losing matter continuously, or is it pretty much a closed system? All right. where does the energy that you use to survive originate, right? So we talked about that energy in the food we get, but where did the energy in the food come from originally? Okay, so we want to be able to explain that. And 4, if some energy is always lost in transfer, okay, do you think it's more efficient to eat plants or animals? And explain why. By the way, these topics right here are going to be our entry task when you guys walk in the door to class tomorrow, all right? So have some thoughts about these. These will be our entry task and some discussion points before I turn you guys loose to try to finish up those lab reports. And then after we kind of wrap up our understanding of where we need to be in terms of energy, we'll start our discussion of ecology and how energy essentially dictates what we see happening in the ecosystems. All right?